Hey everybody, I just wanted to do a quick quiz review. We'll do a quiz 1 review and then I'll do another video for a quiz 2 review. Just for those of you that are getting these answers incorrectly or getting these answered incorrectly so that you kind of know what you did wrong. The first question asks, which of the following is true? And actually you could probably follow along with the quiz if you want to open up 2 browser windows, I suppose. Which of the following is true regarding the hydrogen bonding ability of a single carbonyl group? So let me draw a carbonyl. So here's our carbonyl group. Now the oxygen here has some lone pairs. Now as far as hydrogen bonding goes, there are hydrogen bond donors and hydrogen bond acceptors. Water, for example, can be a hydrogen bond acceptor and a hydrogen bond donor. It can be a donor in the sense when it is around an amine. Let's say that there's an amine group somewhere. Here's the rest of that molecule. It has a hydrogen bond here, a hydrogen that can form a hydrogen bond with this nitrogen. And the oxygen is pulling all these the electron density away from this hydrogen, creating a little bit of a polarity. So this oxygen has made this hydrogen positively charged. Now that makes it attractive to any negatively charged atoms, such as this nitrogen that it's hydrogen bonding to. And so in this case, we can actually see both players here. We can see the donator, the hydrogen bond donator. That's the atom that actually owns the hydrogen. That's the oxygen. So the oxygen here is the donator. The nitrogen in this example is the acceptor. It's able to get that hydrogen as part of its hydrogen bond because it has a lone pair. And that makes it the acceptor. So then when you look at the carbonyl carbon, it's really easy then to see which of the two this is. There is no hydrogen directly attached to this oxygen, so it's not the donor of the hydrogen. It can definitely accept a hydrogen bond, like in the case with water, right? We can form a hydrogen bond between these two right here, if they were close enough, where the oxygen here is the acceptor, and the oxygen here is the donor. All right, that was question 1. Question 2. I guess I don't need to write question 1, question 2 every time. That'll just take more time. Which of the following best describes the interaction that would occur between molecules of CH3CH210, CH3CH210. Let's just start over. I'll just draw it. So 2, 4, 6, 8, 10, 12. This is a 12 carbon molecule. Again, CH3, there's 1 carbon. CH2, 10, there's 10 more, so 11. CH3. So 12 altogether. So they're saying what kind of interactions would happen between these molecules, and so let's just draw another one. All right, so there is no polarity here. We got to remember what our interactions are. They are ionic. They are hydrogen bonds, dipole, and well, there's also ion dipole. But if either of these guys are there, we might investigate that further. And then dispersion forces, sometimes called van der Waals forces, sometimes called instantaneous dipoles. But in this problem, they're called hydrophobic interactions, meaning water hating. And that's the case here. These are carbon-hydrogen bonds. Rest of the molecule carbon, hydrogen bonds. There's very little uneven electron sharing here, not enough to create any kind of partial charges. So nothing other than the fact that these guys both don't like water is going to make them interact with each other. They're both just going to stick together because of instantaneous dipoles that happen with any atom that has electrons. Hydrophobic interactions. Again, you're looking for the presence of charges or ions, right? For ionic, we don't see that here. We don't see a hydrogen attached to an O or an N or an F. Those are the only kind of donors for hydrogen bonding. Those aren't in this molecule. And we don't see dipoles, dipoles being electronegative atoms embedded in here that are going to create areas of partial charge, like a carbonyl. A carbonyl is a dipole. It's got a couple of charged atoms here. Not fully charged like ionic, partial charges. All right, what would be the pOH of a solution composed of 10 micromolar HCl? All right, they want the pOH. All right, you have options. If you know the concentration of hydroxide, we can just say the negative log of the hydroxide is the pOH. Doesn't seem like we have hydroxide though, we have HCl. HCl is a strong acid. HCl is going to dissociate into hydronium and chloride. 10 micromolars, or 10 times 10 to the minus 3 molars, would, is it 10? 10, yeah. 10 times 10 to the minus 3 molar would dissociate into even amounts of both of these, and we would have 10 times 10 to the minus 3 molar. Since we know hydronium ion concentration, we can use the negative log of the hydronium ion concentration to find pH. If we know what the pH is, 14 minus the pH will give us the pOH, because these two add up to make 14. Equals, I don't know what that was happening there, sorry. Equals 14. There's also something we could do if we actually really wanted to use this equation here. We could use the fact that the Kw, or the dissociation of water, the constant for water, is 1 10 to the minus 14, and that's actually equal to the concentrations of hydroxide and hydronium. So since we know the hydronium concentration, we could rearrange this equation and solve for the hydroxide. In either case, you can just plug this number right here directly into this equation for pH, remove, subtract from 14, sorry, and that's what we would get. The pH would be 12 in this case. It's definitely not impossible to determine. Next question. What would be the pH of a buffer solution made by mixing 100 mils? So let's actually draw a little picture here. So we've got 100 mils of 0.4 molar benzoic acid. Let's just call that BA. And we're going to add that to 100 mils of 0.2 molar NaOH. This is going to have the effect of neutralizing our benzoic acid into, so I can draw a little structure here so you can see what we're talking about. So that's benzoic acid, obviously sodium hydroxide. We're going to get the salt of this, the carboxylate ion, because our acid now is going to be missing its hydrogen. This would be sodium benzoate with the sodium there. Let's call that sodium benzoate, and we're going to get some water. Now the question is, what would the pH be of a buffer solution that gets made by adding these two things together? Okay, how did we make a buffer? Well, we converted some of the original starting acid into its conjugate base. Some of this acid is now conjugate base. And when you have any mixture of acid and conjugate base, that's a buffer. Okay, we need to know how much of each we have, because the pH of this buffer is the pKa plus the log of the ratios of that base to that acid. They gave us one more thing. They told us the pKa is 4.2. So we know that already. It's 4.2. We just need to figure out what this ratio is, and then we can add that to 4.2, or the log of that to 4.2. Okay, neutralization time. We need to figure out how many moles of each we have, how many moles got used up, and so on. Now, to do that, we can use this equation. Molarity equals moles over liters. And we can use the fact that we know, let me circle it here, we know the molarity and we know the volume of both of these. Okay, so I'm going to do a real quick calculation here on my calculator on my phone, since I didn't grab my calculator. So I'm going to say that for the benzoic acid, it is 0.4 times 0.1, right? 0.1 liters, which is 0.04 moles. And for the sodium hydroxide, the NaOH, that was 0.2 times 0.1, or 0.02 moles. Okay, so what does this mean? This means that I started with 0.04 moles of that stuff. I reacted it with 0.02 moles of sodium hydroxide. That's going to remove some of my acid. I'm not going to have as much anymore. How much will I have? Well, looks like I'll have half as much, right? Because 0.04 minus 0.02 is 0.02. So that's the new amount of moles that I have, is 0.02 moles of that acid. Now, sodium hydroxide is gone. It got completely used up. But it did convert some of my starting acid into sodium benzoate. So how much did it convert? Well, every sodium hydroxide molecule made one of these sodium benzoates. So I've got 0.02 moles of sodium benzoate. All right, so I've got the 2 bits of information that I need, right? One more step. In this equation, we want to put molarities, not moles. So we should put this back into a concentration, meaning we divide it by the volume, the moles over the volume. Don't forget here, we added together 100 mils and 100 mils. So this is a 200 mil now solution. So the new volumes are going to be for the conjugate acid, it's going, or conjugate base, it's going to be 0.02 moles over 0.2 liters for a grand total of 0.1 molar. For the HA, it's going to be the same thing, 0.02 moles over 0.2 liters for a grand total of 0.1 molar. Okay, we did a lot of math for nothing. We just found that the ratio of these two, of the acid to base, or the conjugate base to the acid, is 1 to 1. They're the exact same. If you plug log of 1 into your calculator, you're going to get 0. So basically the pH is going to be the pKa. So the pH in this case is 4.2. A lot of you got that right. A couple of you didn't get that right. That might have been because you entered back into this into this right here. Maybe you didn't put. Well, actually, if you forgot to, even if you had forgotten to go and recalculate the concentration, and you just used the mole amounts, you would have got a ratio of 1. So something must have happened there in the neutralization step. You guys probably didn't do a neutralization with that sodium hydroxide, or you used the sodium hydroxide number thinking that's the base in the Henderson-Hasselbalch equation, and that's not the case. Which of the following amino acids has no chiral center? Glycine, glutamate, histidine. Okay. All amino acids are chiral and are L isomers. Those are your 4 options. Okay. First off, that one's wrong. And actually, nobody got this one wrong. You guys all got this question right. The glycine's the only one that has 2 hydrogens on the alpha carbon, and so that makes it achiral. So nobody got that one wrong. I don't think we need to talk about that one. Which of the following pairs of amino acid side chains, R groups, could form ionic bonds? So for this one, you have a few choices. You have alanine and what is this? Asparagine? No. Aspartate. Aspartic acid? Aspartate. asparagine. I never get that one right. I'm sorry. I don't have the list in front of me with the three-letter codes, but I'm going to show you how we can easily rule that guy that one out because of this. We have another option. We have glutamine and methionine. We have glutamine and arginine, and then histidine and cysteine. So these are the options, and the question is, which of the following pairs could form ionic bonds, meaning that there's going to be pluses and minuses on their R groups that are going to attract each other. For this, let's just take a quick look at that one slide I had, or that one resource I gave you guys in the first module. So down at the bottom, if you look at the bottom of this list, you see that there is aspartic acid, glutamic acid, lysine, arginine, and histidine that all have a third pKa. So that third pKa means that their R group, right? Because that's the pKa we're talking about. If we jump back here real quick, every amino acid, right, has a acidic hydrogen here on the carboxyl end, has an acidic amino acid, an acidic hydrogen on the amino end at physiological pH especially, but even at low pHs. And then it has an R group, and that R group, this is where the third acidic hydrogen could be. And so only R groups that have acidic hydrogens are going to be able to form ionic bonds. And so you can see they are histidine, arginine, lysine, glutamic acid, and aspartic acid. So if we jump back to the list, we can easily see why we can rule some of these out. Histidine is not on that list. Methionine is not on that list. Alanine is not on that list. So the only set here that has a pair that can both form ionic bonds is the glutamic acid and the arginine. I think I called it glutamine earlier. Glutamic acid and arginine. I never get, and this is my problem. Glutamine becomes glutamic acid, and glutamic acid can lose a hydrogen and be called glutamate. And so sometimes glutamate and glutamic acid are talked about like they're different amino acids. They're not. Glutamic acid is the same amino acid as glutamate. Glutamic acid is just what it is called when it is like a low pH, when it has its hydrogen on the carboxyl side. When it loses it, like at physiological pH, and this is gone, and this is gone, then there's a negative charge there. So this becomes glutamate, or aspartate, even though they are glutamic acid and aspartic acid. Why that confuses me so much all the time, gets me tongue twisted, I don't know. And then glutamine and glutamate, are the amine and the carboxyl version of the same amino acid, and same with asparagine and aspartate. Okay, sorry. Which amino acid can form disulfide bonds when oxidized? Your options are histidine, methionine, cysteine, or both cysteine and methionine. And disulfide bonds are, of course, sulfur-containing. There's only one amino acid that has sulfur in it. That's cysteine by itself. So that's the reason why methionine, though it does sound like it would have... actually, that's not true. Methionine does have a sulfur in it, doesn't it? It just doesn't form disulfide bonds. Yeah. Sorry about that. I was no wonder people get confused. Yeah, methionine does have a sulfur, but that's just it's just not included. Just to show you what I'm talking about. Slides. So where's methionine? So you can see methionine there. Now methionine in that form already has two bonds. So let me jump back and kind of explain. So methionine like this is not the same as methionine like this. Just like if we say, alcohols have high boiling points because they contain, oxygens bonded to hydrogens, they can hydrogen bond. That's not the case with ethers, right? We don't see ethers having high melting points like alcohols do. So this is fundamentally different than this, and this is fundamentally different than this. Different properties, different reactivities. That's why cysteine does disulfide bonds and methionine does not. I hope that was clear. What would be the net charge of the amino acid lysine at a pH of 1? Here you have to worry again about those three groups. You have to worry about the N side. You have to worry about the C side. So I'm going to just start this off at like a pH equal to 1. And that's what they're asking for, pH equal to 1. And then we've got the R group, which in, I don't want to draw it wrong. Let's see, what's lysine? Lysine has, there we go. How many? 1, 2, 3, 4, 5. 5 carbons with 2 amino groups. Oh, my bad, that's not true. 1, 2, 3, 4 carbons with 1 amino group. I hate when they draw them sideways and I'm not used to it. So 1, 2, 3, 4 carbons and this guy. Okay, CH2, H2, H2, H2. Okay, this is a single bond here. All right, this is lysine. Now, at physiological pH of 1, you can see here what is charged and what is not charged. Now, how do you know when something is going to have its hydrogen on it? Well, you go back to this list again, this amino acid pKa list. If you look at lysine down here towards the bottom, it gives us the pKa's for the 3 acidic hydrogens. Above or below the pH that's equal to this pKa, we would expect the hydrogen to either be there or not be there. So below the pKa's, the hydrogen's there. If the pH is above the pKa, then the hydrogen's most likely going to be gone. The pH equals the pKa right at that midpoint. So the first pKa I mentioned refers to the acidic carboxylate side. So this doesn't fall off until about a pH of 2 point something. So this will be here. All of these others don't fall off until much higher pHs. But if they were to suddenly start falling off, we would see the pH change from, the charge change from being a +2 at a pH of 1 to now being a +1 at somewhere between 2 and 3. And then as you continue to raise the pH, then this hydrogen comes off. This positive charge goes away. And now this thing only has 2 charges on it, so it would be neutral. And then at, what was it for lysine? For lysine down here on the list, pKa3, 10.53. So after about 10.5 pH, or almost 11, we're finally going to lose the other hydrogen from that amine group, losing that positive charge and giving it an overall -1 charge, -1 being the only charge it has left. So if you thought this was difficult with one amino acid, wait till the exam when I stick like 5 amino acids together and ask you to give me the overall charge of the peptide. Now keep in mind, if there's a bunch of amino acids linked together, there's still only one N side, one C side, but then there's 5 R groups, right? Okay. So the answer to that was +2. Okay, last question. Which of the following would be true regarding the peptide bond? A, it's planar. B, it can't freely rotate. C, it displays double bond-like character. Or D, all are true. I don't know if those are the actual A, B, C, Ds for those, but those are your options. Now, again, let's kind of line up an amino acid here, or 2 amino acids. So we've got N, C, C, and then we've got N, C, C. Now, we don't need, I guess we do. We need C double bond O, C double bond O, O minus. Let's give this guy the H3 plus, a minus. Okay, here's our peptide bond right here. The nitrogen also has another hydrogen on it. It's got a lone pair hydrogen. We've got some R groups, R1, R2. Okay, this is a dipeptide. Let's look at that what's true about the peptide bond. So first off, is it planar? Well, I don't know. How do we tell? We look at the geometry, right? We look at the geometry around the atom that we're interested in. And so, actually, first let's talk about something. Let's do this in order so it all makes sense. Let's talk about double bond character first. This has resonance, meaning that this lone pair right here under the nitrogen, sometimes this can pop up in here, forming a double bond and kicking out one of these sets of electrons to come sit back up here. And this can flip-flop back and forth, back and forth, back and forth. So let me redraw this sort of, this little square here a different way. Let's draw it like this. I lost my my hydrogen. So something like this. So what we actually have is a little bit of partial double bond character everywhere, because this thing is rapidly changing back and forth between double bond here, double bond here, double bond here, double bond here, right? Back and forth, back and forth, back and forth. So now we've got double bond character everywhere. Okay, so that part's true already in this question. It cannot freely rotate. Well, is that true? What do we know about double bonds? Double bonds form because of overlaps of their orbitals. Specifically, there's a sigma bond, means shared electrons, and then there's some pi orbitals that are overlapping, causing this, what we call double bond. Those pi bonds that form actually stop these bonds from being able to rotate. So we lose rotation. That's the part's true about double bonds as well. So because this displays double bond-like character, it actually does have some limited rotation. In fact, it can't rotate around very much, or you can maybe wiggle, but it's not going to be rotating. To rotate would have to break the bond and break the lining up of the p orbitals, and so that's why it won't happen. Okay, is it planar? Well, if we can imagine having a carbon here, actually we can even picture this, without all of this extra stuff that we've done. Here, that was too far. Well, let me go that far back. If I were to even without the double bond character, if we were to say, what is the geometry around this carbon atom, right? This carbon atom right here. Well, it's got 1 electron group, 2 electron group, 3 electron group. Do you guys remember what we call that? Trigonal planar. The nitrogen would be the same. The nitrogen wouldn't have the same geometry. But because the nitrogen is locked in place, it gives this part of the bond here sort of like a rigid. What the book uses a neat little example. It says that amino acids are like playing cards, end to end, like this. And so this is the peptide bond here. This is the carbon nitrogen bond, and then this is the nitrogen carbon bond, and then the carbon, has the I can't even draw it. NCC. Yeah, this isn't a good drawing. Sorry, guys. But what I was trying to illustrate is that the peptide bond itself is locked in place and planar, and that the bonds that are free to rotate are the ones on either side of the peptide bond. And so it's almost like a bunch of playing cards that can kind of twist around each other, but the bond itself is laying in the plane of the card itself. Okay, so they are planar. This was a bad picture. I think I had a better one in one of the lectures, but all right. So that should wrap up the quiz 1 review video. If you did well on the quiz, good job. If this helps you do better on the next one, then that's my intent. All right, guys. See you next time.